Hey everyone, this is building a mapping language in Go with Parser Combinators and Lockdown Boredom. My name is Ashley Human Being Jeffs and I'm a person, and you can bother me on Twitter at JeffL and GitHub under the same username. Please don't come to my home address. What we're going to be doing in this video is building the parser for a mapping language called Bloblang. And this solves a very similar use case to the very popular JQ language, where we've got structured documents coming in, usually in JSON format, and we want to do some translations to the structure and also maybe some mutations on certain fields. But the language we've got here is more based off a lesser-known language called IDML. I'm not going to spend too much time introducing the language because I want to get straight into the parser, but I'll run through some of the basics. So a Bloblang mapping consists of any number of these statements where we've got a left-hand side assignment target and a right-hand side query. Root on the left-hand side refers to the root of the new document we're creating, and this on the right-hand side refers to the current context, which starts off as the root of the input document. So here we're creating a new field foo, and we give it the value of nested.value from the input document. And we've also got cool variable assignments using the let keyword. So we're creating a new variable here called bar, and we're giving it a static string value. We have support for literals of all the usual types, including objects and arrays. And we can do a load of other cool things like we've got if and match expressions. You can do arithmetic, and most of Bloblang's mutations are done with methods. So it looks very, very similar to JavaScript in a lot of ways. So you might be wondering why make a whole new mapping language? Boredom. Nothing better to do. All valid reasons. I maintain the Benthos stream processor, so as well as that, because that did factor in, I wanted a new mapping language. I mean, Benthos already supports JQ, JamesPath, and Awk for this exact purpose, but I wanted something that was going to have better integration to Benthos internals. So Bloblang is able to do things like metadata manipulation, and also it can do, so Benthos supports windowed processing, and Bloblang supports similarly windowed mapping, which I won't go into here, but is pretty cool. Also, I wanted a language with a bit more of a focus on large mapping. So Benthos is a stream processor, and I love JQ. I use the hell out of it, and I recommend everybody try it out. But the syntax is much more optimized for being condensed, which is very suitable when you're writing it on a command line and executing it in scripts. But in the stream processing use case, we've usually got mappings that are very large, hundreds, maybe thousands of lines, and it's going to be shared across teams. So JQ mappings tend to become a little bit cumbersome and difficult to read. So I wanted something that looks a little bit nicer, more like a conventional programming language. And convenient error handling, I'm not going to go into this. I want to get into the mapping, the parsing, sorry. But yeah, it's got nice granular and also very generic error handling controls. Very fit for production stream processing use cases. So this is what it looks like in action. We've got a mapping at the top. Underneath that, I've got an example input document, and underneath that, I've got what would come out. So let's just quickly run through this. So the first thing we've got here is just a basic assignment. We're creating a new field ID, and to that we query. So this is a coalesce operator. So when you open up brackets on a dot path, you can have any number of these piped fields, and basically the first field that exists and is not null is what gets selected. So author doesn't actually exist in the input document. We've got user instead, so that's what we end up selecting, and then we'll query the ID field of that. And then here's a method. So again, methods are the main way of doing mutations in Bloblang, and this is a type coercion. So whatever the value is, we convert that into a string. The next thing we do is we do a bit of array manipulation. So we've got this input array of strings, and what we want to do is we want to copy that over. So thoughts equals thoughts, but then we call this method filter on that. And the argument that we give this is a query where the context is each individual element. So it becomes the string. So what we call on that is contains. So we want to know if the particular string contains what we're looking for, which is hauler notes. We only want thoughts regarding hauler notes, and that's what we get on the output here. So we have one in this particular input document. And finally, we create a new field, has good taste. This is going to be a Boolean, and to populate that, we have a static array here of lowercase Pokemon names, and these are all Pokemon that have been predetermined to be lit. And what we do is we call contains on that, which checks whether the array contains an argument. And the argument we give it is the fave Pokemon of the input document, and we lowercase that to make it a case-insensitive search. And as you can see, their favorite Pokemon here is Rattata, which is trash. So has good taste in this particular document is false. Now, I would say that this mapping is not good because, as you can see, one of the thoughts here from our particular user is that their favorite Hall & Oates album is H2O. Now that demonstrates fantastic taste, and the field here, has good taste, does not specify that it's for the Pokemon category only. So really, this should have taken thoughts into account because the information is there. So my recommendation is do not deploy this mapping in production. It's not good. Right, so without further ado, that's Bloblang. Let's look at how to implement a parser. So when you decide that you want to write a parser for a new language, the first choice you're faced with is what are you going to use for doing that? And my massive oversimplification here is that you've basically got three options that cover a very wide spectrum. So on one end of the spectrum, you've got a high-level grammar. Looks kind of like this, where you specify in some language specifically designed for specifying other languages what you want to parse out. So for example, this is a JSON parser from Pest, which is a project that I really enjoyed using in Rust. And what you end up with is you've got a formal spec for your language now, and what the tooling does is it generates the code that is actually going to do the parsing. So on one hand, it's cool, you've got this high level spec, you can potentially generate different languages, so you can have parsers in different languages just from this one spec. However, you don't get to choose what the code looks like. So that could be a problem for you in terms of debugging, it could be a problem in just how you use it. And also these high-level grammars, they all have quirks. At the end of the day, there's always going to be something that seems a little bit off or ends up becoming a bit of a headache. And it is another thing that you're going to have to learn and introduce into your project as a build step or something like that. So it swings and roundabouts, but there's definitely a lot of good reasons to use a high-level grammar. Then on the exact other end of the spectrum, there's very low-level code. So this would be you're writing code that manually walks down some input and parses out tokens by hand, and you've got very granular, tight control over the exact path that your code is taking any given time. And now this is specifically very good for if you need your parsing to be super high performance, either in terms of speed or memory management, things like that. This is a JSON parser example from Dave Cheney's blog, where he's specifically writing a parser to be fast, which is exactly when this is a reasonable thing to do. But as you can see, like, you wouldn't be able to read this and mentally have a picture for what the language looks like, whereas with a high-level grammar, that is basically the goal, is to have something that both describes the language and also gives you as a human a good reference for what the language looks like. Now, parser combinators sit basically somewhere in between. This is just code, and you've got full control over the code that gets written. Nothing gets generated, but at the same time, it's trying to look higher level. So you can potentially look at parser combinator code and get a rough image in your head of what the language actually looks like and how it works. And that's why it's not in either category. It kind of sits in its own little space in the middle. This isn't going to be the highest performance code because you're not supposed to have super granular control over the parsing. This is more of an abstraction that makes reading and writing it a little bit easier. And it's also not going to give you a super full picture like a high-level grammar might, because again, this is just code. So ultimately, it's never going to be as concise as a high-level grammar as it describing your language. But you do get some key advantages. So I'm kind of hoping through this video that you'll see firsthand the reasons why parser combinators might be good. In my particular use case, I didn't need the parsing speed to be super fast. I needed the thing that it parses out, the execution engine for the language, to be fast. So performance wasn't a big problem for me. My main concern was I didn't want to add another build step to the repo. This is an open source project. And I just wanted to play with Parser Combinators. I'm going to be honest. Okay, so you've got some stuff you want to parse. You've chosen Parser Combinator to do that. Good for you. Well done. The first thing you're going to have to do now is come up with a common function signature that all your parsers are going to implement. And that's super important because that's how your higher level parsers can compose the lower level ones, is if they all look the same. And what that means at this point is you're going to have to choose what your input looks like and what your output looks like. For me, I chose rune slices to give my parsers. The reason why I want to deal in runes is because I don't want to have to manually deal with multi-byte characters, which is what I would do if I was passing byte slices around or strings. If I pass runes around, then because my input is Unicode text, all that stuff's managed for me and nothing explodes. I'd recommend that for most people unless you're explicitly parsing a binary protocol. And the other thing I do is I only return one parameter back. The reason for that is it just looks a little bit cleaner to me when I'm composing these functions, but you could, if you wanted to, return two parameters and have an explicit error and a success. But for me, I have this common struct and I have to use that to represent either a fail or a success. The way in which I populate it for a success is there's a payload field which contains the resulting payload, and that's an empty interface because I don't know if you've heard this actually, but Go doesn't have generics. One day when it does, I'll be able to go back and refactor all this stuff and have explicit types, but for now we've got an empty interface. Now usually this is going to be a string type from the lower level parsers, but the upper level parsers are going to give us nice structured types, which you'll see in a minute. The other thing we do is we've got a remaining field which is the same type as our input, and the reason why that's important is because parsers only use up as much of the input as they themselves parse, and then it's up to you, the caller of that parser, to give the rest of the input to the next parser in the chain, and therefore it's super important that parsers give you that back because they're the only thing that knows how much of the input they used up. Now in the case of a fail, you might hate all of this. The first thing I do is I've got this error field, and that is an explicit error type. So rather than the generic error interface here, I've got an explicit type. It does implement the error interface, but the reason why I'm doing this is because I want to enforce that all parsers give me this specific type because it contains important information in it that I want to make sure all parsers are giving me when they mess up. And you'll understand that. I'll go into more detail in a minute, but there is a caveat to this, which I'll tell you about. The other thing I do is I've got this remaining field populated again, even when parsers fail. And if you've got a keen eye, you'll know that that is redundant information because when a parser fails, it shouldn't be moving the input forwards at all, which it doesn't. And what we end up doing is we just give it back the input that we were given. But I chose to do this for a reason. There is a reason, but you don't have to follow me here. You could choose not to do that. There's no super important reason for doing that. So the caveat on the error type, so it might not look intuitive because not many people do that, because there is a gotcha. If you have an explicit error type and that's what you're returning in functions, so imagine we've got our parsers and then we have a high level function within the parser package that calls the parsers, that might be tempted to just return this error type. And that becomes a little bit dangerous because if we end up having a higher level function above that, which we give to users, or heaven forbid we give this to users, there's a bit of a nasty here that might be difficult to debug, where if you recast a nil version of that type to a generic error type, what happens outside of that is it looks the same as a non-nil error. You can find out more at this link if you don't understand my explanation. But basically what it means is the thing that converts this type into a generic error interface has to be explicit in doing a check on that error against nil and returning it if it's non-nil. But then if it is nil, it has to return an actual nil over the nil instead of nil, if that makes sense. Hopefully it makes sense. And this is what an actual parser looks like. This is basically the most simple parser we could make. It parses a single character. And what we do is we instantiate our parser by giving it an argument, which is the rune that it's supposed to be parsing. and then what it does is it returns a closure of the signature of all parsers, this common signature that they all have, and inside that we encapsulate the parser logic, and this is super simple. So basically we check that the input is greater than length 0, and we check that the first character matches the rune that we're looking for, and if either that's not true, then we return a fail, and otherwise we return a success. Simple as that. Now in the success we do two things. So first we cast the input rune to a string and return that instead. The reason for that is basically that the more common the results are in your parsers, the more you can deal with those results in a common generic way. So since a rune is very, very similar to a string, it makes sense to make them common, and then what you can do is you can make general tools that say, okay, execute all these parsers and they should all return strings, and then what I want you to do is concatenate the strings. So generally in my parsers you'll see that even if what they're parsing out is like a slice or something like that, they'll return the string representation, and that's kind of common. Obviously the higher level parsers will return structured results, so they don't do that. And then the other thing we do is we return the remaining input, which is always the input moved forward by 1. And this is where like the kind of convenience of slices comes in. So the fact that we're passing a slice around means that all the parsers are doing is extracting the bit that they want, and then they just return the slice moved forwards a few characters. And this is what it actually looks like to use. So here we instantiate a parser by giving it the character that we're parsing, like a $sign. And then what we can do is we can call it with our input, a rune slice, and here we're giving it $hello. And the result payload, when we do that, should be $, because there is a $, and it's the first character. And then the remaining is what's left, so hello. And then the idea is that we could take that remaining result and feed that potentially into the next parser of our language. Or maybe we just stop there because all we want is to parse out our dollar bills, y'all. And that's good enough for us. However, let's go back on this fail. So if you've got a keen eye, you may have noticed that we're feeding in redundant information here, like I said before. We're giving it so we give the error the input, which I'll go into that in a minute. But also the general fail struct, we also give it the input slice. So why do we do that? It's because I'm lazy, basically. So in a hypothetical scenario where, imagine we've got a parser where we feed it multiple parsers, and so in this case we've got two, thing 1 and thing 2. And basically we don't care whether the first parser succeeds or not, we just want to execute it, and then we want to feed whatever it results in into thing 2. And that's actually quite a common pattern. So imagine if thing 1 is a white space parser. Most of the time when we're parsing out white space, it's optional. So we don't actually care whether the parser itself succeeds or not. If the input doesn't have white space, we just want to continue. But if it does have white space, we want to move along and then parse what comes after it. So if I can always assume that remaining, regardless of whether or not a parse succeeds or fails, is exactly what I want to feed into the next thing, then I can skip checking whether that particular parser failed or not. So if there was a chance that it would fail and therefore remaining wouldn't be populated, I would have to execute thing 1 and then check whether it succeeded or failed or not to know whether or not I'm feeding remaining into the next parser or just the input unchanged. Whereas with my assumption that all parsers, even when they fail, populate remaining, I can get away with this. Look at that. Look how sleek that is. I think overall, in hindsight, this has probably saved me maybe a couple lines of code. So I'm not sure whether I would recommend doing that if you're writing your own Parser Combinator library, but it's what I've got. It's what I'm going to stick with. And that's that, basically. So let's take a look at the error type. So this is the explicit error struct that all parsers have to return if they fail. And my reasoning for that is it should always be possible to locate an error. And my mechanism for doing that is this error type. So let's break this down a little bit. So we've got a struct which contains expected, which is an array of strings. The purpose of that is to contain any number of tokens that we would expect at the point that we're parsing. So if parsing fails for any reason, it's always going to be because we expected something and we didn't see it. And I don't think that's ever not the case in parsing land. There's always something that could have been there that would have made things okay. And the purpose of that field is to just populate it with all the things that we expected as candidates. And then what you're able to do is, so in this hypothetical error string function, the real one is more complicated than this because it gives better output. But having that array populated means you can say, oh, my parsing failed and I wanted this instead, you idiot. The next thing that we populate is the input as it was where the error occurred. So any parser always knows what the input was when it got called. What it doesn't know is what the entire input was, because it's only seeing the next bit. It's only seeing what's left in the input string. However, what we can do is we can store that in the error type, and then whatever calls the entire parsing chain, when it gets an error back from that parse, what it could do is it could potentially call a function like this, where it provides the full input that got given to the parsing. And then you could do things like you can infer from that, based on the length of what it gives you and the length of what the error had when it occurred. You know exactly where in the input the error is. And that allows you to create nice error strings like this. So this kind of format has become like the sort of de facto standard here when you're printing multi-line error messages from parsers, because it gives you quite a lot of nice context. But the important thing that we're able to extract from the error is the line where the error occurs and the particular character where the error happened. And that's kind of the error type here. So I'll be expanding on this in a minute because it does become a little bit more complicated than this, but that's the important meat of it. And oh, look at this. So this is the older sibling parser to our char parser. It's called term, and basically this is when we want to parse out a combination of characters. And as you can see, the constructor here, we take in a string parameter just because it's more convenient, but then the first thing I do is I extract the rune slice, and that's critical for doing comparisons within the parser, because again, we don't want to be dealing with multi-byte characters manually from that string. Now the first thing we do in the body of our parser is we just check that the input we're provided is actually long enough to contain the term, and if it's not, we can error out immediately. But otherwise we'll walk each individual character that we're looking for, and we'll just make sure that the input character equivalent matches that. And if not, we return our fail, just like before. And in the event of a success, we return so what I'm returning here is the input parameter string, because we want to escalate a string up the parser tree. So we might as well just use the one that's already there, rather than creating a new one. And the other thing we do is we move the input slice forward specifically by the length of the term in runes. So again, that's where extracting the rune slice is super important, because we want to make sure that we're comparing apples with apples here. We're not going to move by an unpredictable amount when we've got multi-byte characters. And what it looks like to use, oh, it looks nice. Oh, look at that. So we instantiate our term. Here we've got a static string foo, and if we give that foo space hello, a very common input, we get out as a payload the string foo, and then what's remaining is space hello. Oh yes. So this is the first combinator-ifying combinator function of our parsers so far. So everything before is just parsing out a particular piece of text. This is a parser that takes children parsers. And this is where parser combinators as a concept start to come into their own, because this is kind of why you jump through all these hoops and have all these consistent interfaces. So this is one of, there's loads of different ways you could name this particular parser, but basically we give it a list of parsers to try, and it will go through each one, and the first one to succeed is what gets returned. And if none of them succeed, then we return an error that kind of combines all the errors of the parsers that we attempted. And I'll show you, we also have a concept of a fatal error, which I'll go into in a minute. But basically, here's the instantiation. We have a variadic parameter here, so we can have any number of parsers. You could instantiate this with 0 if you wanted to. And then what we do is we walk each one. So we get an input, we go through each parser individually, we try it out, we get a result. And if the result is, if there's no error, then it succeeded and we can return it. Or if it did return an error and the error is fatal, so you haven't seen that method yet, I'll go into that in a second, but if the error is fatal, then we return immediately without even trying the other parsers. But don't worry about that for now. So assuming that's not the case, we've had a non-fatal error. What we do is first we check, so we keep track of the errors of all the parsers. And the way in which we do that is we have this preserved error as we walk our child parsers. And if that's nil, then it means that this is the first parser we've tried that's failed. So we can copy it straight in. We just take it as it is. Or if one of our previous parsers has failed and we've stored the error, however, the position of the error, which we can infer by looking at the input field, is further along, then we can actually consider that to be the preferred error. So imagine we're trying to parse out a couple different things in the input string, and if one of the parsers fails immediately but the other parser fails a little bit further on, then that's the more useful one to provide users potentially, because that kind of implies that that was the route that they were trying to go down, and they've obviously messed something up further along the way. So it doesn't really make sense to show both of those errors if one of them managed to get further. However, if there's already an error that we've stored, this isn't the first error that's failed, and they're in the same position, then what we can do is we can combine the errors. And again, this is a method that you haven't seen yet. I'll show you in a second. And what that means is that we can return to the user all the context of all the parsers that have failed when we provide an error message, which potentially makes it more useful. And assuming that we never hit a parser that succeeds, we return our fail with the stored error. And this is what it might look like to instantiate. So the interesting thing for you is to look at, so we've got our one-of parser, and then we give it any number of child parsers. So here we've got 3 terms, foo, bar, and baz. And if we give it an input that matches one of those, so bar space hello would match, then what we get back is exactly the result we would get from that individual parser and nothing else. And that is the same for the remaining slice that comes back. So this is exactly what we'd expect if we just instantiated a bar parser and nothing else. So let's talk about fatal errors. So this is the same error type that I showed you before, except I've expanded it slightly because the previous time I showed you the error struct, I was lying to you, because that's not what it looks like in my code base at all. This is still a lie, but this is less of a lie. And the main difference is that we've now got this field, which is a child error. So our error struct can now wrap other errors. And the assumption there is that if there's an error that we've wrapped, then this is something fatal. So this isn't just, we expected to see a particular thing and we didn't, and therefore maybe another parser is able to successfully parse the thing out. This usually implies that we have correctly parsed the user's input and it's fundamentally wrong. So the example I've given you here at the bottom is that we've successfully parsed out a method. So here we've got a correct method syntax here, The syntax is correct, there's no grammatic errors here. However, it's just the fact that the method itself does not exist, and therefore it's not useful in this particular case to try another parser, because we know what the user has given us. It's a method, it's just that's wrong, okay? And that's what makes it fatal. Basically, there's no point trying anything else out. This is it, this is the problem. Let's just immediately escalate that to the user and tell them what they did wrong. And this is fatal. Method is literally just, is the error that we've wrapped nil or not? Simple as that. And this other method that I've added is add, where we take another error. And what we want to do is we basically just want to combine the contexts. So we've decided that these are two errors that parsers have hit in the same position, and therefore the context that either of them has ought to be combined into one error, and it can all be presented at the same time. So when we do that, the expected tokens just gets expanded. Simple as that. And if the error that we're adding from doesn't have a wrapped error, but the error that we're adding to it does, we'll copy that as well over. But I'm not actually sure how common that is. It's just something I kind of figured we ought to do as well. So on the subject of error handling in parsers, we've got this slice of expected tokens. Sometimes that's something we want to override. So in the case I've given you here, we have a closing bracket parser, which is just a character. Now, if we just used that on its own and the parsing failed, the error message that we give back would have that character in it, which is kind of ugly. It's not particularly useful. It doesn't read as well as if we had the words closing bracket. So what we can do is we can define these kind of meta parsers that just wrap a child parser. And this one in particular is called expect. And what that means is we wrap a parser and we're explicitly saying what we expect on a higher level. So we instantiate here a closing bracket parser, and if it fails, we override the expected array to be what we write here, which means our error message is now expected closing bracket rather than just expected symbol. And it's just nicer for everybody involved. It's nicer for me, it's nicer for you, it's nicer for them. So why not? Okay, so now we're really starting to move up in the language stack with our parsers. So this is a Boolean parser where we expect one of the terms true or false. And what you'll notice I've done here is, so I'm instantiating a parser that is a one of these two terms, and then I wrap the overall thing with this new expect token, which is just Boolean. So what would have happened is one of would have combined, in the case of a parsing error, the tokens true and false. So we would have given an error message expected true or false. So what I've done here is I've overridden that, and now we'll just say expected Boolean, which is just generally cleaner. And what you'll notice is I've instantiated a parser, and I'm calling it pattern, outside of the actual function itself. So we don't instantiate it every single time this parser gets called. We can statically create it when the closure gets returned instead. And the body of this is super simple. So basically we execute the pattern that I created, and if it fails, then we can just return that straight away. If it succeeds, then what we do is, because this is a higher level parser, we don't just want to return the string of the contents. What we want to do is we want to actually return the Boolean itself. So we want a true or false result, not the string true or the string false. So what I can do here is I can just cast, I know that payload is a string. This is technically a potential for panic, but in my case here, I know this is going to be a string, so taking a shortcut here, cast it into a string there, and then I won't need to do this when we can use generics. This can just go away, so don't worry about it. And then all I do is I just check whether it's true, whether it's the string true, because again, if the parser didn't fail, then the string is either true or false. There's no other possibility there. So if it is true, then we return true, otherwise we return false. And then I make sure that my success struct is also given the remaining from the underlying result from the raw pattern. And this is what it looks like to use. So we instantiate Boolean, there's no arguments, so we instantiate the parser here, and then we can give it some input. So this is true and this. And the resulting payload is actually a Boolean type, like I said. So in this case it's true. And the remaining is what's left, so and this. And that's that. Okay, so this is a parser that is one step more above our Boolean parser. So this is a query literal parser, and this will be one of the sub parsers of a more generic query parser, where it's essentially a query that contains a literal value, and the literal values it could contain is either a Boolean, which is the parser I just showed you, or it could be a number, quoted string, a null type, it could be an array or an object. I'm not going to dig into those individually because they're basically the same as Boolean. And then inside our function, we do the exact same as before. So we just call the pattern that generally describes what we're looking for. And then it's within the success that we actually create the higher level construct from whatever that pattern gave back. Now in this case, we are now at the point where we want to return an actual query type, which is something that's actually going to get executed by the Bloblang execution engine. I'm not going to go into what a query actually looks like as in its interface, because it's kind of out of the scope of this. I'm just kind of focusing on the parsing side of things. But what we do is we call a constructor here a new literal query. So what gets returned from that is a structure that implements a generic query interface, and what we provided is the empty interface payload of all of these types. And what's going to happen is that will just get placed within the tree of our mapping, and every time it gets queried, it's just going to give a copy of the static literal value that it's holding on to. All the parsers up until now have only parsed out a single token from the input and returned the result, and that's it. But in reality, anything that we want to parse is going to be a series of parsers extracting different bits of the input. So this is the low-level parser that is kind of a convenient way of doing that, called sequence. And the way it works is you provide it with a series of parsers that you want to happen in order, and what it does is it starts off by creating a result struct where the remaining field is the input, because then what it does is it walks each parser and it provides that parser with the remaining slice of that struct. So it starts off as the input when we're on the first parser, but then what happens is because we assign the result struct with the result of the current parser, it means that every time we move on to the next parser, we're feeding it the remaining slice from the previous one. And obviously if it fails, then we return immediately, and the error that we return already contains the correct position where the error occurs in the sequence. But if it doesn't fail, then we append the result to a slice of results, and at the end, assuming none of the parsers have failed, we return an overall success result with all of our payloads. So what we're returning back is a empty interface slice containing all the parsed out tokens from the sequence that we've been given. So this is what it would look like to use it. So we have a sequence instantiated. In this particular case, we're parsing out a Boolean and then a space character, and then a quoted string. So if we fed it something like this, we've got a Boolean true, quoted string, and this, and then we follow that up with some more text. What will actually get parsed out in our resulting payload is an empty interface slice containing true, the space character, and this. So this is the inner contents of our quoted string. So we unquote it when we return the payload here. And then in remaining, we still have what's left afterwards. So the sequence will parse just like any other parser. It'll parse as much as it wants to, and then it gives you back what's left afterwards. And this is a let statement parser. So now we've moved quite far up the stack. This is what it would look like to define the parser for a specific let something equal a query statement. And what we have to begin with is we instantiate a sequence. And the important bits are we expect the term let, because that's the keyword that begins our let statement. Then we have a var name. So this is just an unquoted string parser. So basically alphanumeric characters and an underscore and you can possibly have some other characters in there as well. But the purpose of that is to just be explicit about which characters can be included in a variable name. So I separate that into its own parser just to keep it nice and managed. And then we follow that up with the character equals, which is mandatory. It's something equals something else. And then we follow that up with the general query parser, which I haven't shown today. That's maybe one for a future video, but that would include our literal query literal parser that I've just shown you. And what you'll notice that within our sequence, I separate each of the actual terms that are important with these whitespace parsers. So whitespace could include spaces, tabs, new lines, all that stuff. It's kind of up to you, and it depends on the situation as well. And you'll notice that some of these are optional. So I've also defined a meta parser similar to expect called optional, where if the parser that you provide it fails for a given input, what it does is it basically says, no, it didn't, wipes the error away, and the payload that comes back is just null. Because we don't care. We don't care about the result. We just want to move the input forward. And what this means is that the first whitespace between let and our variable name is mandatory, because obviously this is an explicit token. We want to make sure that exists and it's not just part of some other expression. The other whitespace is optional in this particular example. I don't think that's actually the case in Bloblang. But basically I made it optional because as long as you've got a variable name and then you follow it with equals, which is assumed to not be valid in a variable name, and then we can also make the whitespace after the equal sign optional if you wanted it to be, but you can have it if you want it. Now I could create a sequence meta parser that assumes that between each parser you provided there is optional whitespace, and then you wouldn't have to include all the whitespace when you instantiate it. But I like the fact that you can be granular about what types of whitespace are allowed between certain terms and where they are and are not optional. So I haven't chosen to do that myself. Now when we run this parser, we execute the pattern just as normal. So if it errors out, we return immediately. But when we are successful and we extract the result, it's going to be an empty interface slice. Now, when there's generics, this will potentially look a little bit cleaner. But for now, we've got all these nasty type coercions. And again, I'm not doing explicit checks here to see if the type is valid, because I know that it's going to be an interface slice. But obviously, if you want to make this super tight, then you would have type checks around all this stuff. But basically, I extract the slice of these sequence payloads into a variable, and then I extract from that the variable's name from this parser, and then finally I take out the query function, which is this query function interface type, which I have chosen not to show you for now, from this parser here. And then what I can do is return my success result, where I create a new let statement. So again, this is a super high level type, which is actually the thing that's going to get executed when Bloblang gets run. And what we're doing is we're telling it the variable name to assign when this gets executed, and we give it the query function to execute at that point, which is going to give us the thing to populate our variable with. And this is kind of pseudocode-ish stuff I've put out just to kind of show you what this looks like on a high level. So if we instantiated a parser here, and we gave it something like this, where we've got let foo equals, and then the quoted string hello world, and then some other stuff at the end, the payload that we get back is equivalent to this. So we instantiate it with the variable name foo, and we create a literal query, because this is a string literal here, where the contents are a string hello world, and there is some remaining stuff, so we would expect to get that back as well. If we were going to pass something like let bar equals true, similarly we would have a let statement. We've got a literal query with a true payload, and the variable name in this case is bar, and in this case we've finished, so there is no remaining runes. And in the case where we might have some sort of error, so for example we've got a syntax error here, we might get an error message like this where it says failed to parse mapping, line 1 char 9, and we expected an equal sign. Now I could have, if we go back on this, so you see my char parser here, I could have put expect equals as a string there to make this error message look nicer, but in the example here I didn't, and I've got no regrets, to be honest. Not going to guilt me. And I'm pretty exhausted by this point, so I think that's it for now. So I haven't covered the whole shebang. That's kind of just a general walkthrough of what combinators look like. Again, the purpose of this isn't to tell you whether combinators are a good idea or not, whether it's the right choice for your parser library. I just kind of want to show what it looks like and some of the considerations when using them. And hopefully you're an adult and you can make your own mind up as to whether or not that's what you want to do. Here's my details again. My name is Ashley Jeff, so you can bother me at JeffL on Twitter. And if you're interested in the language itself, Bloblang, and how it gets executed, then you can find out more at benthos.dev. I'll put the links in the description as well. And if you want more videos like this, I can dig more into this, but I'm really not sure if I can be bothered. But if you're interested in that, then give me a thumbs up and maybe leave a comment specifically as to what bits you're interested in. Thank you for watching.